I have undergone an embedded system internship at EMERTXE Information Technologies, and during this internship, I have worked on the project Simulation of Washing Machine using PICSIMLAB. The contents of this project comprises of introduction, objective of this project, requirements, and implementing the project in embedded C language, which consists of data types, variables, pointers and memory management, control structures, functions and modular programming, and preprocessor directives. We have specifically used PIC16F877A microcontroller in this project, which consists of 40 pins. We have used MPLAB XIDE as the code editor, XC8 as the compiler, and to demonstrate the output we have used PICSIMLAB. We have also used some of the hardware peripherals like LED, CLCD, fan, buzzer and digital keypad. We know that washing machines are widely popular nowadays as they solve the most basic and common problem of daily household, that is cleaning clothes. Here, washing machines come into rescue, combining convenience, efficiency and providing better hygiene. Nowadays, fully automatic machines are more popular than semi-automatic machines. Let's know what is embedded system. An embedded system is a specialized computer system that is a combination of both hardware and software, usually designed to perform specific tasks. In essence, embedded systems are the hidden computers that make many of the devices and systems we use daily function as intended. They are designed to perform specific tasks efficiently and reliably within the context of a larger system. Embedded systems are classified on the basis of functionality and performance. On the basis of functionality, embedded systems are classified as real-time, standalone, networked, and mobile. Based on performance, embedded systems are classified as small scale, medium scale, and sophisticated. The project mainly focuses on replicating real-world washing machine functionality in a virtual environment. Here we implement the project using embedded C, and for demonstration purposes we use PICSIMLAB. We get a comprehensive understanding of washing machine components, cycles and operations. So let's go through the basic functional requirements of this project. Here we have used CLCD as a display and buzzer for alarming conditions and also as a motor. The first one is power on screen. We have used SW5 as the input. When SW5 is pressed, the machine is turned on and the output shows powering on washing machine. The second one is a washing program screen. Here we have used SW5 and SW4 as the input. Using the keypad SW4, we can scroll between the options available like daily, heavy, delicates, white, stain wash, eco cottons, etc. And a long press of SW4 will select the option highlighted with asterisk. The third one is the water level screen. Here also we have used SW4 as the input. Using the keypad SW4, we can scroll between the options available. A long press of SW4 will select the option highlighted with asterisk. The options mainly here are auto, low, medium, high and max. For the start screen, we have used SW5 and SW6 as the input. If SW5 is pressed, the machine is started and the function selected is displayed, and also the time taken is also displayed. And we get switched to function screen. And if SW6 is pressed, we go back to the washing program screen. The fifth one is a function screen where we have used SW1, SW5 and SW6 as the input. Here the process mainly is we have to display the function and the time leaped. If SW5 is pressed, the washing machine is started, and if SW6 is pressed, we have to pause the washing machine. And the status of SW1 is indicative of the door status. When the switch is pressed, it signifies that the door is open. Conversely, when the switch is not pressed, it indicates that the door is closed. The final completion status screen Here, once all programs are completed, we get a display, program completed, remove clause on the CLCD. Coming to the embedded C, the C language is very important for embedded systems due to its efficiency, optimal resource utilization, portability, and many other advantages. It basically comprises of data types and variables, pointers and memory management, control structures, functions and modular programming, and preprocessor directives. So, as I said before, we have used PIC16F877A microcontroller in this project. The main specifications of this microcontroller, as it has 40 pins, it has 5 ports in total. Port A consists of 6 pins, port B, C and D consist of 8 pins each, and port E consists of 3 pins. It supports serial communication as it has 2 pins, TX and RX. It can also support SPI protocol, and the oscillator frequency range from 4 MHz to 40 MHz for this microcontroller. So now let's come to interrupts. An interrupt is a signal that temporarily halts the execution of the current program to attend to a higher priority event. Upon receiving an interrupt, the CPU saves its current state, jumps to a specific memory location, then containing the ISR or interrupt handler that executes the ISR to address the event and then restores its previous state. This mechanism is crucial for real-time responsiveness, allowing the system to efficiently handle asynchronous events like button presses, sensor data acquisition or communication protocol activities without constantly polling. Let's come to the timers now. Timers are indispensable components in embedded systems, acting as precise timekeeping devices that enable accurate scheduling and control of events. This allows the embedded system to perform tasks periodically, create precise delays, generate waveforms like pulse width modulation for motor control or dimming LEDs, and even serve as the basis for real-time operating systems by providing system ticks. So let's come to the basic software requirements of this project. The first one is the PICSIMLAB X IDE. We have used it as a code editor, XC8 as a compiler, and for demonstrating outputs we have used PICSIMLAB. Let's know what is LEDs. LEDs in embedded systems are used due to their simplicity, low power consumption, long lifespan and fast switching capabilities. They serve primarily as visual indicators, providing immediate feedback on system status, errors or operational modes, example power on or off, network connection, battery low, etc. Coming to the digital keypads, these are common human-machine interface components in embedded systems. They are typically arranged in a matrix of rows and columns. These keypads minimize the number of input-output pins required on a microcontroller. When a key is pressed, it creates a connection between a specific row and column. The microcontroller scans the keypad by sequentially activating rows and reading the corresponding columns. So let's know about CLCDs. These are commonly seen as 16x2 or 16x4 modules. These are widely used in embedded systems for displaying text-based information. They are relatively inexpensive, simple to interface with microcontrollers, and consume low power. They typically use a parallel interface requiring a set of data lines and control lines to send comments and data. Fans in embedded systems primarily serve the critical function of thermal management, actively dissipating heat generated by internal components like microcontrollers, processors and power regulators. Excessive heat can degrade the performance, reduce component lifespan, or even cause system failure. A buzzer in an embedded system is an electromechanical device used to generate audible alerts or tones. It acts as an output indicator, providing non-visual feedback to the user or signaling an event within the system. Now let's go to the project implementation part. After loading the hex file, the display shows press key 5 to power on washing machine. So let's press SW5 and we get the display as powering on washing machine.
and we get switch to washing program screen, where we have options like daily heavy delicates, eco cottons, whites, etc. And we can scroll among them through SW4 option, and a long press of SW4 will select that option with asterisk. Here we have selected whites, and then it get switched to water level screen after the selection. And here also we have 5 options in the water level: auto, low, medium, high and max. And you can scroll among them through SW4 option, and here I will select medium, and a long press of SW4 will select it with asterisk, and we get switched to next screen after the selection of the option. So see, SW5 is for start and SW6 is for stop. So let's press SW5 for starting the program. See, the next screen will show program whites and the time taken. Now the function has started and the time taken is also shown, and here we use 5 for stat and 6 for pause. We can use SW1 for door lock status, as if that the door is closed or open. We can know from SW1 option. And here before loading the hex file, we have to change the board as PICSIMLAB. And here the fan is used as a cooler and the buzzer is for alarming conditions. So after the completion of the function, the buzzer will buzz and the display will show program completed, remove clothes. So let's wait for the completion of this. See, the program is completed and we get switched to washing programs. So as we have come to the end of this project, the washing machine implementation using PICSIMLAB, that successfully demonstrates the integration of hardware and software to automate and optimize the washing process. By incorporating peripherals, microcontrollers and user interfaces, the system efficiently manages water levels and wash cycles based on the fabric type and load size. The project not only enhances user convenience and energy efficiency, but also highlights the practical application of embedded systems in modern household appliances. Thank you.